Right, so there's some resources already on this subject, but I just wanted to go through or give you a video explanation, so you've got a kind of somebody talking through it rather than just having to read it. And if you're struggling, it might make a little bit more sense of the other resources. But there's lots of examples of this on some of the sheets that you've got access to. So make sure you do read through it, because understanding how to apply the equation of a straight line and y equals mx plus c to a graph in order to plan an experiment is tricky and not I won't say it's not straightforward. It is dead easy, but it's not something that people pick up straight away. And if you're not really sure about it, you can struggle quite a lot. So I'm just going to show you a really simple example first, and again, all these examples I think are on the sheet as well of what we're actually really talking about. So let's say take an equation for, again, it doesn't really matter what any of these symbols are because they're literally just algebraic. It's an algebraic process. But this is voltage, current, and resistance. Now, I'm going to write a little bit thicker, I think. So let's say that we were doing an experiment where we wanted to find a value for resistance by measuring the voltage and the current of something. Okay, so what we might do is plot our voltage and current values on a graph, something like this, and then you're going to forgive this line of best fit because it's not going to be particularly straight and it really should be drawn with a ruler, but this is a quick sketch. So the gradient of that would of course be change in y over change in x, which for us is change in voltage over change in current. And voltage over current from our equation is equal to R. Alright, so we're looking at that general process, but what you need to do, that's if you've already got your graph and you're figuring out what to plot, what you need to be able to do is, in advance of that, figure out, in order to get the thing I want to find, what do I need to plot on my graph? Okay, so this is where you start with an equation. So let's do it for the same equation so that you can see the same idea. The equation of a straight line is y equals mx plus c. So this is the general equation of a straight line. Obviously y is your y-axis, so this is a variable. X, of course, is your x-axis, so this is a variable. This is your gradient, and therefore is a constant, because it's the equation of a straight line, so by necessity that's a constant. And this is the y-intercept. Now both m and c could be things you want to find in an equation, in an experiment. Now obviously y-intercept also constant. But 9 times out of 10 it's the gradient that you're going to use. It won't necessarily be the gradient you want, but you'll use the gradient to then work out something else. So you need to go through a bit of a process to figure out, okay, in the planning stages of my experiment, what's the end game? What do I want to find? What graph do I need to plot in order to find that? What raw data do I need to collect in order to be able to plot that graph? And you've got to work through those questions. So you're kind of starting at the end and working backwards so that you know what you've got to start doing. And then, and only then, can you write your procedure to plan to collect all of the things you need to collect. So y equals mx plus c has broader uses than this, but I'm just looking at it from an experimental point of view for the planning stage of writing your procedure. Now, it's important that you don't put any of this stuff in the procedure. This is just what you do on a bit of paper first to figure out what your procedure needs to be. You'll talk about some of this later when you do the analysis, but you don't put it in your procedure. You just need to think about it in advance. Right, okay, so let's say the aim of this experiment is to find R. That's not a great aim, but I'm not getting into writing aims and other things now. This is all about y equals mx plus c. So the broad aim is to find the resistance. Okay, so what I do is I take the equation that would give me R, and if I'm at the stage of planning my experiment completely from scratch, I'm not given an equation, I can take any equation for R. But v equals I would probably still be the one I'd pick. So this would mean, okay, if I can then compare this to the equation of a straight line. Right, so equation of a straight line, y equals mx plus c. Right, firstly, figure out from your equation what are your variables and what are your constants. So I could change the voltage and I could therefore measure the current as a result of it. So this would be my dependent variable, and this would be my independent variable. And the resistance I'm going to look for would be the resistance of a resistor, say. So that would be my constant. In my equation of a straight line, that's my variable, that's my variable, that's a constant, that's a constant. So the way we do it is we take our equation and we arrange it into the form of y equals mx plus c. So this is the simpler version. There is an extra complication we need to think about. I'm going to worry about that in a second. Now, it's already pretty much there, but it does just need rewriting a little. Not much, and literally what I'm going to do is this. I'm just going to write the I and the R the other way around. There is no plus C term. There is no y-intercept. Effectively, it's a plus 0. Now, that's interesting in its own right, because that tells me it should go through the origin. It won't. They never do, and you should never force it to. But you know that it should, and the fact that it doesn't will tell you about your experiment, and can be talked about in the analysis phase. Okay, the reason I've written R and I the other way around, you might go, well, what's the point? They're the same thing. They are the same thing, that's why you can do it. But we do it so that I can match them very specifically to each other. So that would mean that V would be my y-axis. And if the current is my x-axis, that leaves R as the constant must be the gradient. So therefore, if I was to plot voltage on the y-axis, current on the x-axis, get a straight line, the gradient of that straight line would tell me here what the resistance is. In fact, in this case, it's really nice because it would tell me what it is directly. Now, there's one problem with this. In one way of looking at it, what you plot on the graph is irrelevant. We're actually not studying the graph. We're using it as a tool to get a gradient to find m. It's just a part of the calculation. It's irrelevant. It doesn't even go in the results section. It would probably just go in the appendix of a lab report. It's not really important. But there is also the convention that we would normally plot the independent variable, the thing we control, on the x-axis, and the dependent variable, I don't know why I put ID there. Independent variable would have been IV, but would have made more sense. Let's put IV. Independent variable on the x-axis. So that's the thing we control, all right? We set that. And the dependent variable is the thing that changes as a result of it, would go on the y. This is just the convention of how we plot graphs. Now, if we were to do that, that would really mean that what I should do is plot, bring that down, what I should do is plot my independent variable, which would be voltage on the x-axis, and my dependent variable, which would be current that would change as a result, on the y-axis. Okay, so what does this mean? Well, what it means is I need to rearrange my equation. I had V equals IR. I want it in the form y equals mx plus c, and it already looks like it is, but I've just decided that I actually need to put my x and y somewhere particular. So I need to rewrite the equation in a way that matches. So what I do is I put the variables in the places. I don't rearrange for this, I just put them in. So what I've said is my y-axis now is current, and my x-axis now is voltage. And I rearrange the equation to make that work. Now, if you've got squares and things in the equation, then one of these might end up having to be time squared rather than just time, and so be it. That tells you then that you'd need to plot time squared on that axis, and so that's what you do. In this case, it's not so complicated. But in order to get R next to V, I would need to divide by it. I'd need to take it down there, divide both sides by R effectively, but basically take it underneath and divide by R. So to rearrange this properly, I'd need to do that. Now the problem with that is, well, you're still at the unfamiliar stages with y equals mx plus c. That's not very helpful. So here's what I do, slightly differently. There's no difference between that and what I'm about to write, except that one of them I will mess up and the other one I won't. V divided by R is the same as 1 over R times V. It's exactly the same thing. But now I can match up my variables and constants a little bit better to the general equation of a straight line. I is my y-axis, tick. V is my x-axis, tick. And that means that if I have a gradient, that gradient, I don't know why we have sound effects, but we do. That gradient is going to be not resistance, but 1 over resistance. So when I come to do the analysis part of this experiment, then if I want resistance, I'll work out the gradient of the graph, and I'll do 1 divided by that gradient to give me the resistance. And this is where you get the extra little nuanced bits in. Trying to fit your equation to the equation of a straight line, but with the x's and the y's and the right way round, trying to get your dependent and independent variables the right way round. It's a bit of a convention, and in some cases it's a bit needless, but whatever is derived from your independent and dependent variables generally is considered it should go on the x and y axes. It's not a biggie, I think, if you end up doing something slightly different, but you should always strive to do that where you can. Again, it's just following a convention, even if that is a little bit, I don't want to use the word daft. Right, let's just do one very quick other example, which would be the example from the lab diary, which is the pendulum. So the pendulum equation, which is the time period of a pendulum, is 2 pi times root of L, which is the length of the pendulum, over g, which is the acceleration due to gravity. So this tells us how the time period for one swing depends on the length of the pendulum. Now, quite clearly, this isn't in the form of a straight line. And also, incidentally, if we were to plot t against L, we would not get a straight line. In order to get a straight line, t would need to be proportional to L, and it quite clearly isn't. Okay, so if we square both sides of this, you can do it with t and root L in fairness, but you don't have to. If we square both sides, so you can do it with t and root L, but if you square both sides, it's just a little bit more neat. So square both sides gives us t squared on the left, 4 pi squared, and then it just removes that square root, L over g. Right, so one of the things then to do is work out what your variables and constants could be. So time would be a variable. If I change the length, I'm going to get different times. So that's my other variable. 4 pi squared is by definition a constant, they are just numbers, and acceleration due to gravity is also a constant. You'll notice there's no plus c term. I've effectively got plus 0 over there, so we wouldn't worry about a plus c term, and that is, again, 9 times out of 10 is going to be the case. Okay, so what's my independent variable and my dependent? Well, the thing I'm going to set would be the length. So this is my independent variable, and my dependent variable, therefore, is the time that it would take for it to swing. Okay, so what I now need to do is get this in the form of y equals mx plus c. I need to rearrange it. Well, to believe it or not, it's already pretty much there. What it needs is rewriting slightly. Well, that's all. So my independent variable should go with x. So L should be there. My dependent variable should go with the y. So t should be there. And then basically what I'm going to do is see what falls in that space next to the L, because whatever it ends up there is going to be my gradient. And hopefully it's going to contain g, and I'm going to be able to use the gradient to find g would be the end game. We've got a problem. There is no way I can rearrange this equation to get just t and just L. I can get t squared over here, some stuff, and L. Or I can get t over here, some stuff, and the square root of L. So that's what I've got to do. Now, I've already squared the equation at the beginning, which should give me an indicator. What I need is t squared. Genuinely, though, if you did this in terms of root L, it would work in exactly the same way. It's just, this is one of the common equations we do a lot. So, with t squared on my y-axis and L on the x-axis, if I just rearrange this equation, and literally all I've really got to do is bring this g and rewrite it over there. That's all I'm actually going to do. So the 4 pi squared is already there in the right place. Don't forget the squared. And if I write the g under there instead of under the L, algebraically it's identical, but it now just makes a little bit more sense. So my y is t squared, my x is L. So if I plot length on the x-axis, time squared on the y-axis, that should, because t squared is proportional to L, t and l are not proportional, but t squared and l are proportional. That'll give me a straight line. And the gradient of that straight line will be 4 pi squared over g. So now what I can do is I can plan an experiment to collect values for time and length, and I can finally get on with writing my procedure, knowing that this is my end game, this is where I'm heading. And when I've got this graph, I can work out the gradient. Once I've got the gradient, I can just rearrange this equation, and this is where everybody goes wrong. They forget they've done all this work and then they try rearranging the equation for the pendulum. That's not the point. You're working out from the gradient to the graph. Make sure you're using the gradient to the graph. Don't go back to the original equation. Otherwise, there's no point in doing the whole experiment. You might as well just take one reading. So if I rearrange that equation I've circled in blue, I just get 4 pi squared divided by m, which is the gradient. So my value for g would be 4 times pi squared divided by the gradient of the graph. So bear in mind, I'd need to work out the gradient, I need to plot a graph. To get a graph, I need a range of readings. If I need a range of readings, I need a procedure to let me collect a range of readings for time and length. And I'll need to calculate t squared out of those repeat readings. So now you're in a position to go away and write your procedure. So that's the basic outline of what you do with y equals mx plus c. The more you can practice doing this with a few different equations, so have a look at those sheets that have been provided. There's various sheets giving you some examples of this, how you can do this with different equations. Once you've got the idea of this with a few equations, you can honestly do it with anything. It's all just about getting a straight line. And the final word is, why do we need straight lines? Quite simple. You can't look at a curve and tell if it's a quadratic or an exponential. You just can't tell. It just looks like a curve to you, whereas a straight line we can do. If we get things in the forms of straight lines, we can check equations and we can work out constants. Nice and easy.